So in this video we're talking about equilibrium. This is chapter 15 in the textbook. So we've talked about equilibrium as dynamic equilibrium with phase change. We're going to apply the same principles to reactions. So when we have a reaction going in the forward direction as well as the reverse direction, both directions are occurring at the same time when the rates of both of those reactions are equal. The reaction is in equilibrium. Alright, so it's still dynamic because we still have the forward and the reverse directions occurring. We're constantly having reactants turn into products, products turn into reactants, but because it's at equilibrium and the rates are the same, there's a constant amount of reactants and a constant amount of products. And this goes back to what we talked about with our rates of reactions. For example, if we have O2 plus NO producing NO3 as our equilibrium reaction, we could write the rate of our forward reaction as our rate constant K times our O2 times our NO going forward, and at equilibrium that would equal the rate of the reverse, which would be some other rate constant K times our NO3. So setting those two rates equal to one another and then rearranging to solve for our rate constant K's gives us a ratio of our products over our reactant concentrations. The ratio of the rate constant forward and the rate constant reverse is equal to the equilibrium constant, KEQ. So KEQ for equilibrium is a capital K. Rate constant K is the lowercase k. Now the law of chemical equilibrium allows us to calculate what this ratio is, or what this K equilibrium value is, based on that ratio. So our products multiplied together raised to their exponents, which would be their coefficients, divided by reactant concentrations, also raised to their coefficients. Now when we calculate this K equilibrium value, we get a numerical value for the ratio. And this is a constant value at a given temperature. So for a particular reaction at a given temperature, our K equilibrium value will be constant. The K value could also be any numerical value greater than 0, moving all the way up to infinitely large. So our K equilibrium is never negative, because we can't have negative concentrations, but it can be very, very small if we don't have very many products, or it can be very, very large if at equilibrium our reaction is mostly products. When we're writing our ratios, we have a couple of rules that we follow. The first one is going to be that we want to put products over reactants, and the coefficients from the balanced equation become the exponents. So N2 times O2 squared, because we have a coefficient of 2, divided by NO2 squared, which also has the coefficient of 2. We only include things in the gas phase or the aqueous phase. Alright, because those are the type of reactants or products where the concentration can change. If we have solids or liquids, their concentrations are constant and are related to their density. But gases and aqueous components can change concentration, so we only include those in the K equilibrium expression. So if we have 2HBr liquid forms H2 gas and Br2 gas, we only have H2 times Br2 for our expression. We leave off the HBr because it's a liquid. When looking at the K equilibrium expression, we can measure this in terms of concentrations of our reactants and products, and this is sometimes referred to as the Kc value, or we can measure it in terms of pressure if we have a gas reaction, and this is referred to as the Kp value. Both of these are K equilibrium expression values, but they are using different units to measure them. So we can have different numerical values, whether we're using molarity as concentration or atmospheres as pressure units. Alright, so how do I know which one to use? If I have a reaction that has mostly aqueous components, I have to use Kc. Right, so I can't do the pressure of an aqueous component. I have to use concentration. Concentration has to be in molarity. So Kc is used the majority of the time. Anything that has aqueous in it, we have to use Kc. Sometimes it is just referred to as the K. If my reaction is completely in the gas state, or I have solids and gases, but no aqueous components, I can refer to it as a Kp and measure my concentration in terms of pressure units. Right? For a gas, the pressure is proportional to the concentration, based on the ideal gas law that you hopefully remember from previous class. Pressure times volume is equal to moles times R times temperature. If we rearrange to solve for pressure, we see that pressure is proportional to the molarity, so our N over V would be our molarity. So we can use pressure units just like we use concentration units. And there is an equation that helps us relate Kp and Kc values. Kp is equal to Kc times RT raised to the delta N. So in this equation, R is our gas constant, measured in liter atmospheres per mole Kelvin, because we're looking at changes in pressure and volume. And our temperature has to be Kelvin. Now the delta N refers to moles of gas, and our delta refers to change. So we're looking in the change in the moles of gas from the reactants to the products. Basically, we're trying to determine, is our reaction making more moles of gas, or do we have less moles of gas in the products compared to the reactants? And if we look at this equation, if our change in moles of gas is 0, so either we don't have any gas moles at all, or there's no change, we have the equal number of gas moles on the reactants and the product side, then RT raised to 0 becomes 1, and Kp is equal to Kc. However, if there is a difference, we will get different numerical values for Kp and Kc. And in the next video, I work through some examples on how to do that math. Alright, well, what if we're not at equilibrium? What if we start out with our reaction at initial concentrations, or we have mixed our reactants and products together in unknown quantities? We may not be at equilibrium with our reaction, so how do we know? Reaction quotient Q is the same expression or ratio that we have for K equilibrium that allows us to calculate the ratio when we're not at equilibrium conditions. Okay, this is just calculating our concentrations raised to our coefficients at any point in time. This can be initial conditions, it can be later conditions at any point that's not necessarily equilibrium. And if we look at what Q is representing, we can see how it can be helpful for determining our equilibrium. So if we look at this graph, hopefully this graph looks familiar to you because this is a reaction rate graph. So we have our concentration on the Y, our time on the X. So as our reactant is decreasing in the blue, okay, we see a decrease in concentration. Our product is forming in the pink, so our product values are increasing. And when we first start out, we have only reactants. So in this particular graph, we're looking at N2O4 as our reactant, producing 2NO2. So when we start out at time equals 0, we have only reactants. Reactants are decreasing as we create products, and then our NO2 product is increasing. So what's happening to our ratio? When we first start out, since NO2 is 0, our Q is equal to 0. Alright, since our K equilibrium must be greater than 0, our Q is less than K. But as our reactants decrease, so that's our bottom number, and our products increase, that's our top number, our Q ratio gets larger. So as we're moving in time to the right, our Q is getting larger and larger until it reaches equilibrium, where Q is equal to what our K equilibrium constant would be. At this point, our reaction is at equilibrium, so we see the concentration of products level off and be constant, and the concentration of reactants becomes constant, because now we're at equilibrium. And our reaction will stay at equilibrium until something else happens to make it change. So at this point, Q is equal to K. So as long as Q is less than K, our reaction was going toward equilibrium and continuing to move to the right to make more product. Once it hits equilibrium, now both processes, the forward and the reverse direction, have equal rates, and so all of our concentrations are constant. So we have three different possibilities for the relationship with Q and K. Q can be greater than K, in which case we've passed up equilibrium, and our reaction needs to go back toward reactants to reach equilibrium. We have too many products. Q can be less than K, where we're not at equilibrium yet and our reaction is continuing in the forward direction until it reaches equilibrium. Or Q can be equal to K, in which case we're at equilibrium and our reaction will remain there until something happens. Now if we know the Q or K value for a particular reaction, we can also calculate what Q or K would be if our balanced reaction changed in some way. So for example, if I know the K equilibrium value for a forward reaction, I can calculate the K equilibrium value for the reverse, because it's just the reciprocal. So K equilibrium of a forward reaction is equal to 1 over K of the reverse. If I add two equations together to get a third equation, very much like we did with our mechanistic steps, I can calculate the K equilibrium of the new reaction based on adding the two reactions together by multiplying the K values together. Or if I need to multiply an equation by a coefficient. For example, if I need to double everything, then I know I can calculate the new K value by using that new factor. If I was doubling everything, my factor would be 2 as the exponent. So for example, if I have F plus O2 creating FO2 is my reaction, and I know that K is 0.2 for that reaction, I can then calculate K values for the same reaction under different effects. So I can double everything in my reaction, so multiplying by a cofactor of 2. That cofactor becomes an exponent, so I'll take my original K value and square it, and then this will be the K value of the new reaction. Multiplying by a fraction or dividing, we can do the same thing. So if I'm halving everything, the 1/2 becomes the exponent, and I can calculate my new K value. If I flip the reaction, so now my products become reactants, and my reactants become products, I just take the reciprocal of the K value, 1 over 0.2, to get the new K value of 5. Any combination of these can also be used in order to calculate what the new K value would be. Alright, and here's an example of adding two reactions together and then multiplying the K values to get what the new K equilibrium value would be. So N2 plus 3H2 to give you 2NH3 is our first reaction, and here's our K value. We're going to add it to this second reaction of ammonia and water, and here's our K value. When we add those two together, okay, here is our new reaction. Nitrogen plus H2 gas plus water gives me the NH4 plus and OH minus. What is the new K equilibrium value for this reaction? We just have to multiply the two K values from the reactions we added to get what our new value would be. Alright, in the next video we look at doing some of the math, calculating our K values from our concentrations or pressure values, converting Kc and Kp, and also working with manipulations of K and Q.